This chapter jumps around a little bit. Every other video we've had so far has talked about earthquakes, but now we're going to talk about Earth's interior, and in the next video we're going to talk about how the surface of the Earth is deformed. So we'll jump around a little bit, but hopefully everything will make sense by the end. When we look at Earth's interior, we'll notice that the Earth has really distinct layers to it. Starting from the innermost part of the planet, working our way outwards, we have our iron core. It's a core that's made almost entirely out of iron, but there's a little bit of nickel. We have an inner core that's totally solid, and then we have an outer molten core around it that's a liquid and is capable of flowing. On top of that, we have our mantle, which is really high-density rock. On top of that is the crust. That's the really rocky area where we live. On our crust, we also have our water, all of our oceans and our lakes. And then on top of our crust and our oceans, we have our gaseous atmosphere. But when we look at our planet, it's dynamic. It's constantly changing. Both the mantle and the crust are always in motion due to plate tectonics. It's not fast motion, but over millions of years, it's a lot of motion. And by moving this material around, it's constantly recycling the Earth all the way from the surface down deep into the interior of our planet. Humans have never been deep inside of the Earth. And it's also at too high of temperatures and pressures for us to ever send any kind of instrument inside of the Earth. Instead, the only way that we have any idea what's going on deep inside of Earth's interior is by seismic waves, or those energy waves that are released from an earthquake. And remember that we have those body waves that move through the interior of the Earth, where we have the P and the S waves. And they move differently. Our P waves are compressing things, they're changing the volume, and they can move through solids, liquids, and gases. Our S waves, though, change the shape of a material, so they cannot travel through liquids and gases, only solids. So when we're looking at these different types of seismic waves that are released in an earthquake and looking at how they travel through the Earth's interior, it helps us figure out the different layers of the Earth and how they're different from one another. We'll see that at boundaries between layers, like the boundary between the mantle and the core, that some waves are going to be reflected. They're going to kind of bounce off the surface. Others are going to be diffracted, where it's going to be bent. And it's diffracted a lot when it encounters some kind of obstacle. But by looking at these different types of seismic waves and the ways that they can move through different locations in our Earth, it gives us a lot better understanding of how thick these different layers are and what they're composed of. Early after the Milky Way, the galaxy that Earth is in, started forming, Earth started to accumulate as a planet. And the way that this happened is that lots of really hot molten material started to accumulate or glob together. So Earth just kept getting bigger and hotter. But Earth was so hot very early on that it didn't have any solid surfaces. Instead, it was just one large, basic ball of magma out in space. And here we're going to see that the different elements either rose or sank in Earth due to their densities. Just like with a liquid, if we start mixing liquids of different densities together, like water and oil, they'll separate into different layers based on their density. Early on in Earth's history, when everything was still a liquid, it did the same thing. And we see that our densest, our heaviest elements sank towards the center. So all of the really dense iron and nickel sank to the center and ended up producing our iron core. We see that really buoyant elements, like our silicate, our salty elements, rose towards the surface and created our crust, which is why silicates are the most common minerals in our crust. And this is just called chemical differentiation. Based on the different densities or masses of these different elements, the heavy ones sank towards the center of the Earth, whereas the really lightweight ones rose up towards the surface, towards our crust. So early on in our education, we start teaching children that the Earth has 3 layers: the crust, the mantle, and the core. And these layers are distinct from one another based on their chemical composition. We're going to see that the crust is really lightweight elements, our core is really heavy elements, and the mantle is in between them. But instead of just looking at the chemical differences of Earth's layers, we can also look at the physical differences of Earth's layers as well, whether they behave like a solid or a liquid, and the strength of each layer. Starting with our outermost solid layer, we have our crust. This is the thinnest layer of Earth, and it's very rocky. But with our crust, we divide it into 2 different types, our oceanic and our continental crust. Our oceanic crust is going to be really thin, but really dense, because it's made out of those mafic minerals, the ones that are really dark in color. They're very heavy in weight. They're very dense, all because they have those metallic elements inside of them. On the other hand, our continental crust is twice as thick. It's also buoyant, so it likes to float instead of sinking, and our continents are mostly felsic. They're made out of that granite-like rock that's light in color, light in weight, because it's made out of those salty silicate elements. Underneath our crust, our next layer is our mantle. And unlike what we're taught most of our lives, our mantle is actually solid. But what's weird about this solid is that it flows very slowly. So it's just easier to tell people it's a liquid. But it really is a solid. And the mantle makes up most of the volume of our Earth, or over 80% of it. So we're going to see that there is a major chemical change between the crust where we live and the mantle below us. As we get deeper in the Earth, these rocks are going to start getting denser and heavier the deeper that we go. So our mantle is a heavier chemical composition than our crust is. But we can divide our mantle into the upper mantle and the lower mantle. The upper mantle, closest to the crust, is mostly made out of a mineral called peridotite. This is an ultramafic mineral, meaning it's green in color because it's almost entirely iron in its composition. So we're going to see that the upper mantle and crust is our lithosphere. This is the really rigid areas that makes up the plates of our surface. So it's basically a really cool in temperature, really rigid shell that make up our plate tectonics. But farther down in our mantle, we have the asthenosphere. This area of our mantle is partially melted. That's because it's deeper in the Earth where it's a lot hotter, so these rocks aren't going to be completely melted, they'll just be partially melted. And we're going to see that the asthenosphere, this partially melted part, moves totally independently of the solid lithosphere or upper mantle above it. But even further into the center of the Earth is our core, and this is made up of 2 elements, of iron and nickel. And our core is the densest, heaviest part of our planet. And we can separate our core into 2 layers as well. We have an outer core, which is close to the mantle, that's liquid. It's going to be able to flow around, and it creates Earth's magnetic field that protects us from all the things flying out around in space. But the inner core, the innermost layer on our planet, is a solid ball of iron.